All right, today we are going to look at vertex form. So hopefully you've had a lot of good practice working with multiplying binomials, and you've had your worksheet checked off by Mr. Clay. Now what we're going to do is kind of intro what we're going to be doing next class, which is graphing parabolas or quadratic functions in vertex form. And we've already looked at this when we were in our transformation, so a lot of this is going to look really familiar. We're just adding a little bit of vocabulary that we didn't have before. So first of all, when we have this quadratic function, this U-shaped function, it's called a parabola. So you'll hear me call this a quadratic, or you'll hear me call this a parabola from time to time. And there should be little arrows up there. All right, similar to what we saw before, remember we had our transformations, and we always put this point that's right here in the middle. And that's really helpful because it allows us to see what's going on either side. And now what we're going to do is identify a couple more points that are on this parabola. So notice if we move to the left, so towards the negative numbers, we have the point negative 1, 1, negative 2, 4. So we're going to put negative 1, 1, and negative 2, 4. Going in the other direction, we have the point 1, 1, and we have the point 2, 4, and we have the point 3, 9. We also have this point negative 3, 9. And we talked about before how this is the graph of y equals x squared. It's our quadratic function. And notice what's happening. I'm putting in negative 2, squaring it, I get 4. When I put negative 1 in, if I square negative 1, I get 1. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So what's happening is that we have this middle point right here that only has that output once, but then after and before that, they're complete mirror images of each other. They copycat. Right? Our outputs are 1, 4, we'd expect 9, 16, 25, and then the same thing in the opposite direction. And so what ends up happening is we can put any value for x in here that we want. So our domain is all real numbers, or negative infinity to infinity. But our range starts at 0 and then only does the positive numbers. So we have an inclusive 0, and then we're going to infinity. Let's mark up a couple of things in this graph that we haven't looked at before, and then we'll get a better idea of what's going on. So we have this point right here. I've alluded to a couple of times this name, but it is called our vertex. And then notice that it's where our graph, our slope, or our rate of change rather, is negative or decreasing all the way down to this point, and then my graph starts to go up. So it's kind of going down, 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 down. I get to this point, it changes, and now it's going up, 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 up. So if you relate that to physics, and you throw a baseball up in the air, it's that point where the baseball reaches the top and then starts to come back down, right? So that's our vertex. Then we have what we call our axis of symmetry. And our axis of symmetry goes right through our vertex, and we're going to use a dashed line to represent our axis of symmetry. And notice that it's going right through right here. So my axis of symmetry, I drew right there. And the reason we call it our axis of symmetry is because it splits my graph in half. So it's symmetric over this line. So that line is my axis of symmetry. And the other thing we're going to look at is concavity. And we've already kind of been talking about this as well, but in a different context. So right now my graph is concave up because it's that happy U, right? It's opened upwards. Concave down is going to be when I flip my graph upside down and it reflects over the x-axis, then my graph will be concave down. So concave up makes a U, Concave down is like an upside down U. So we're going to start by looking at our graph in vertex form because that's what we've already looked at our graph in when we were looking at transformations. So an equation is in vertex form if it's in the form f of x equals a times x minus h all squared plus k. And this is the form that we were already looking at again before with our transformations. And so when it's in this form, our vertex is always going to be hk. And this point represents either the minimum or the maximum for our function. So for example, our vertex right now would be 0, 0. If I move to the right 2 units, I'll have a vertex of 2, 0. So it's wherever that point lies. And you guys have already found this vertex time and time again when we were looking at those transformations and looking at how that movement happened. Our axis of symmetry is going to be the equation. So this is going to be x equals h. Because what's happening here is all of these lines, anytime I draw a vertical line, it's always x equals something. So in this case, it's going to be x equals 0 because everywhere on this line, my x value is 0, right? This would be the point 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So since every single spot on that line, or every single coordinate on that line has an x value of 0, the equation for a vertical line is x equals h. And this is the line the parabola reflects over, or is symmetric about. All right, going back to transformations, our horizontal movement is our h value. So we find our horizontal movement in this x minus h piece. And so just as a reminder, this is always the reverse of what you think it's going to be. So it's going to be if we have x plus 2, it means it's moving it to the left 2. If we have x subtract 2, it's going to move to the right 2. So my horizontal movement is represented by my variable h. My vertical movement is represented by that variable k. And that's that constant that's hanging out at the end. And it follows exactly what's going to be happening. So let's say that we had x squared plus 3. That would mean that it's moving up 3. Notice that it's not, again, it's not inside this function, it's on the outside. Whereas this x minus h is on the inside, right? That's being squared. That's part of my function. This is on the outside of the function. Last but not least is my concavity. So concave up and concave down. Concave up, so I'm always looking at this a value to look at my concavity. A function is going to be concave up. It's going to look like a u. And that's when my a value is greater than 0. So there's no reflection. It's going to be concave down when a is less than 0, and that's because there's that reflection over the x-axis. We're not going to dive super deep into the graph stretching. We'll talk about it next class when I'm there, and we'll definitely graph ones where our function is stretching up or down. So this a value may not just be -1, it may be -2, it could be 5, it could be a lot of different values. We're really going to focus on, though, whether it's positive or whether it's negative, and then we'll talk next class about what that a value actually does to my function. So let's look at these graphs on the back side and just identify our vertex, our axis of symmetry, and whether my function is concave up or concave down. So in order to do that, we look at our function and we go ahead and we find this point right here. This point is my vertex, and then I'm going to go ahead and then I'm going to draw that axis of symmetry that goes right through my vertex. So my vertex is going to be this ordered pair, so 3, 0. And my axis of symmetry, which I just call AOS for short, is going to be x equal to whatever my h value is, which in this case is 3. And since this is the U shape, I know that we're dealing with a concave up. Some other information, my domain for parabolas is always all real numbers, and my range is starting at 0 and going to infinity. So from this graph, I was able to say what my vertex is, what my axis of symmetry is, the fact that it's concave up, and then I know my domain and my range. Let's look at another one. For this one, notice that it's shifted up 2 units. So now my vertex is right here. I didn't move horizontally at all, right? I just moved vertically. And so my vertex is the point 0, 2. My axis of symmetry goes right through here, which is my line x equals 0. This function is concave up. My domain is all real numbers, because that's what it's always going to be for my parabolas. And my range, notice that my y values are starting at 2, and then I'm going to positive infinity. So 2 to infinity. Right here we have another parabola. I want you to go ahead and identify your vertex. This is the ordered pair 2, 3, which means I moved to the right 2 and I went up 3. My axis of symmetry, go ahead and draw it right in there. It goes right through my vertex and splits my graph in half. That's going to be really helpful as we start to graph these ones that are a little bit more complicated. So it's going to be x equals h. My h value is 2. My k value is 3, so x equals 2. This one's concave down because it's upside down. My domain is all real numbers. And my range, this time I'm starting at negative infinity. And I'm going up to 3. So I'm going negative infinity to 3. If you want to pause the video and give this one a try on your own and then check your answers, that might be a good idea. So for this one, we have shifted to the left 2 units and down 5 units is where my vertex is living. So my vertex for this guy is -2, -5. My axis of symmetry, again, goes right through, and it's x equals h. My h is -2, so x equals -2. This is concave up. My domain is always, for these parabolas, all real numbers. I can put anything into a quadratic function. And my range, it starts at -5 and then it goes to positive infinity. So -5 to positive infinity. Now let's take a look at these and see without the graph if we can identify a lot of the same information. We're just going to do our vertex and axis of symmetry here. So looking at this g of x function, I'm going to think about how this is moving. This is moving, since it's x plus 3, it's going to move to the left 3. And then I have negative 4 on the outside, so then it's going to move down 4. Which means my vertex, if I'm moving to the left 3, that means it's negative 3. Down 4 is negative 4. And again, we looked at this before we were looking at transformations. That's because this inside piece is like x minus a negative 3. And since it's x minus h must be negative 3. And then once I have my vertex, my axis of symmetry is always x equals whatever my h value is. Well, my h value is negative 3, so x equals negative 3. And we can say that this one is concave down. The reason I know that this is concave down is because of this negative 2 right there. So because my a value, because I have that reflection, well, actually we'll add that right there. Because I have that reflection as a part of my transformation, it's going to be concave down instead of concave up. All right here, looking at my transformations first, it's another reflection. And then I'm moving to the right 6 and up 10. So my vertex, if I'm moving to the right 6, that's a positive. So 6, up 10, 10. So 6 comma 10, which means my axis of symmetry is x equals 6. And since there's a reflection, it's concave down. For this one, we're moving again because this is x subtract h, and my h is telling me how many units to the left or right I'm moving. It's going to be 1 unit to the right, so right 1. And then it's plus 3, so it's going up 3. So my vertex is 1, 3. My axis of symmetry is x equals h. My h value is 1, so x equals 1. And because 5 is positive, it's concave up. Last one, I have x plus 5, which again means like x minus a negative 5. So my h value is 5. I'm moving to the, my h value is negative 5. I'm moving to the left 5. This is a subtract 8, so I'm going down 8. So my vertex, left means negative 5, down means negative 8. Notice those are the exact values that are right here, negative 5, negative 8. And then my axis of symmetry is going to be x equals negative 5, and since 2 is positive, we're concave up. All right, so these notes will be in classroom as well. And we're going to go ahead and keep graphing with these functions next class. But now we have all the terminology down, so we can dive just into practicing and really getting good at graphing quadratics in vertex form.